Hello. Let's go ahead and get started on a lecture on substitution of indefinite integrals. So what we've seen before with integrals is we've seen some sort of rules like the power rule, exponential rule, logarithmic rule, things of that nature. And today we're going to actually talk about more of a method of how to solve integrals. And it'll actually, as we'll see, it'll kind of be like the chain rule, but for integrals. It'll be undoing the chain rule per se. So just so that we're all clear, a very common term, a very common saying instead of saying substitution of indefinite integrals, or even just saying instead of saying substitution, is actually saying u substitution. We're going to see this in a second. We're going to use the variable, the letter u, a lot here. This is just me sort of saying, hey, some people will say this. I'll say this a lot. So if I say u substitution or if I say substitution, we're talking about the same thing. So let's go ahead and get into it. And I want to first start off with an example that I'm going to kind of build up to this idea of substitution. And let's look at this integral. So from what we've seen so far, this integral looks fairly simple, but from what we've seen so far, it's actually a bit harder because we can't explicitly use like the exponential rule because we have this plus one up here, and that doesn't fall under that format of that exponential rule. And so we have to come up with another way of doing this. Now, for something like this, you could probably look at this and just say, hey, just by looking at this, it's going to be e to the x plus 1. Because if I take a derivative of e to the x plus 1, I get the same thing, e to the x plus 1. And now let me be clear, I am doing chain rule. So for this e to the x plus 1 that I'll underline there, and I'll underline that e to the x plus 1 in red just to make a distinction. And I'll try and match my colors up appropriately. If I were to take a derivative of the blue e to the x plus 1, what happens here is I'm definitely going to get this red e to the x plus 1. I get the same thing. I copy it down. But I also have to do the chain rule, which says I multiply by the derivative of x plus 1. Well, what we notice here is that the derivative of x plus 1 is just 1. So, I mean, I could write a multiplied by 1 there, but we don't really need to. It's just 1, so we don't have to do anything. And so as you see, we obviously get the derivative of this blue e to the x plus 1 is the red e to the x plus 1. So this works. This integral, we know the answer to it. But really, there is chain rule that's involved in here in doing this. And we just get a little lucky that in this scenario, it's a little bit easy that we can just kind of look at our answer and say. But what if I made this a little bit more complicated? And in the way that I'm going to make it more complicated, I'm going to make sure that this chain rule portion isn't just 1. And I can do that by just slightly changing this to, instead of e to the x plus 1, I can make it e to the 7x plus 1. Now, if you tried to do this by inspection and just say, all right, it's an exponential, let's try just copying this down. Also back here, I probably should have had a plus c. I just realized that. Plus c. So here, I would have my e to the 7x plus 1 just as a guess. Well, if I try this and I take a derivative of this and see if I get that, I actually don't. If I take a derivative of, and again, let's underline this in blue and this in red, just to, because I have multiple e to the 7x plus 1s. If I take a derivative of this blue e to the 7x plus 1, what you'll notice here is that I do get the red e to the 7x plus 1, but there is a chain rule term that is not just so simple as 1. It actually ends up being 7. And so I end up getting not quite what I'm looking for here. I'm basically off by a factor of 7. So in this scenario, you might be able to look ahead and say, all right, we'll take this 7 and Instead, let's just kind of multiply by a 1/7 here, and that would work. That would get us our answer. But more, what I want to talk about is how do we actually deal with this chain rule term not being one? Because I can guarantee you, in other cases, in harder cases, it's not going to work out perfectly where this is just a 7 and you could recognize, all right, let's just add or multiply a 1/7 in here and we're good. What if this chain rule term, instead of a 7, what if it was like an x squared? That just makes it really complicated and tough. So this idea that, all right, I have a complicated integral that it doesn't match up with my just simple bland exponential rules, because it doesn't match up right there, I have to use what we call substitution. And so what the chain rule is to derivatives, substitution is for integrals. So basically, if I have a derivative and I were to do chain rule on it, if I take an integral, it's kind of like undoing that chain rule. And let's go ahead and look at an example here. So I'm going to do a slightly different example than that exponential. I'll let you go back and work on this exponential here on your own time. But I want to do another example here. And so we're going to see 2x plus 5 to the 7. And we want to take an integral of this. When I look at this function, I notice that I've got a whole bunch of stuff in here, but let's say we just covered all that up. This to me looks like something raised to the 7th, which to me looks a lot like power rule, right? Maybe I just replace all of this with an x, right? And I just say, hey, all of this right in here, it looks like x to the 7th, right? And so this looks like power rule to me. So let's go ahead and write that over on the side. We'll just say, hey, power rule, and we'll put a little question mark next to it. But the problem is that the power rule states integral of x to the n dx, and that's what I'm allowed to use it on. And this doesn't look like that, and the reason is because this x in here, instead, it's actually a 2x plus 5. So what I have to do is I have to do what we call substitution. Basically, I'm going to replace that 2x plus 5 with another variable temporarily, and then I'm going to do my integral, and then I'm going to come back to the 2x plus 5. So a lot of this notation is going to seem weird, but bear with me. We're going to do a handful of examples, so hopefully the notation will get a little bit more, you'll get a little bit more comfortable with it. But the very first thing that we're going to do is, and actually let's go ahead and just write this out. So I have the integral of 2x plus 5 to the 7th dx. So the very first thing that I'm going to do is I am going to say, all right, that 2x plus 5, I kind of hope that it's just an x, right? We can see that right there. It would be really awesome if it was just an x, because then it'd just be like x to the 7th. If it was just one variable, then I could just explicitly use the power rule and I'd be done. So what I'm going to do is I'm going to come up with another variable, and I'm going to call that variable u right there. And that variable is just a placeholder for 2x plus 5. If it's more comfortable for you to think of it this way, you can think of u as a function. You can think of it as u as a function of x is 2x plus 5. I will say this type of thinking will be helpful when we talk about substitution of definite integrals. So this might be good to sort of keep in the back of your mind. But basically, I just like to think of u as a placeholder here. So we've got u as a placeholder, and then what we could do is we could just say, all right, I've defined that. Now let's take this integral here in the blue, and let's just say, all right, equals, I'm going to go ahead and erase this over here. We don't need that. Equals u to the 7th, right? It's just a placeholder. So I just replace 2x plus 5 with u. And then I still have my dx, and this is where I see an issue here. So if I were trying to do this integral, the problem is that it looks like an integral that has a bunch of u's in it, so the variable being u, but this dx is stating that the variable of integration is x, not u. And that's an issue, because when we have an integral, we have to make sure that we're integrating with respect to the variable that is stated, in this case, x. But I don't have any x's in here, I just have a u. So what we have to do is we have to come up with a way to change this dx. And it's going to be very similar to what we did where we changed this and got rid of it. basically, in this definition of u here, I can take a derivative of it, and the notation is going to be a little bit weird. If I took a derivative of this, we might say du dx. I'm going to go ahead and write this actually off to the side. I might have du dx equals just 2, right? If we have u equals 2x plus 5. Instead of using u prime, I'm just going to use du dx. So we don't need that there. So du dx equals 2. Well, we're going to get a little bit fishy here. I'm not going to go ahead and explain why we can do this or the reasoning behind it, but I can sort of multiply this dx over to the other side. That's a little bit fishy. I won't go into why we're allowed to do that or why we want to do that, but that's really what we're going to do here. And so now really what I'm going to write is du equals 2 dx. But I will say, and we'll see this on future examples, you'll probably get to the point where you'll just go straight from u to du. You'll take this and you'll do your derivative of it, and then you'll just write a dx at the end of it. And that's fine. We understand that we're taking a derivative to get from 2x plus 5 to 2. That's the big sort of point right there. And so now I actually look at this. I could do one more step of algebra here, and I can solve for dx. And this actually gives me both a way to get rid of the 2x plus 5. I can replace it with u, and I can get rid of the dx by replacing it with du over 2. And so, and actually, I'm gonna rewrite this as 1/2 du. That'll be a little bit easier. It'll be a little bit better. So now I don't have this issue anymore with this dx. Basically, what I can do is I can just, instead of writing a dx, I can write a 1/2 du. And I do a little bit of simplification, and I end up with 1/2 u to the 7th du. And this is an integral that the power rule is acceptable to use. I can use my constant property and pull that 1/2 out. I just have u to the 7th du. If it's easier for you to think about it, you could think about it instead of u's, you could think about it as like 1/2 x to the 7th dx. Obviously here, I don't necessarily like thinking about it with x's because we already dealt with x's over here. And like we said, u is a function of x. So really it's just, you're going to do this integral the same way you would do this integral. It's just a different letter. And that's why I actually emphasized before in a past lecture about that the letter here doesn't matter. I could put a $sign, I could put a frowny face. It doesn't matter as long as I'm consistent all the way through. So here at this point, we would do our power rule, and our power rule states that we're going to add 1 to the exponent. So I get 8, and then I divide by that resulting exponent. Don't forget a plus c. So then if I simplify, I'll go ahead and put parentheses there. I'm going to have 1/16 u to the 8th plus c. And let me be very clear, we are not done. Even though we have evaluated the integral, we are not quite done because the original integral was in terms of x's, and we have our answer in terms of u. So we actually want to take this u and replace it back in with the appropriate x's. And this again alludes to that sort of thinking, that notion that u is a function of x. U is equal to 2x plus 5. So I can do that right there. And right here, we will be done. This will be our answer. And hopefully what you can see here is that we've kind of undone the chain rule, right? If I were to take a derivative of this, I would multiply the 8 down so that I would bring the 8 down. I'd sort of flick it off the top, as we've said. I would have 8 over 16, which is 1/2. 2x plus 5 to the 7th. Notice how that looks right there. And then I have a 1/2, but I have a chain rule derivative of 2 here. And I know I said a lot there. Basically, all I'm saying is take a derivative of this. You'll notice you get this. And so that's what substitution is. Basically in the red, this is substitution. All of that. We'll make a little note. So Substitution. And you'll see why sometimes we call it U substitution, or even U sub. People will say for short, just for shorthand, they'll say U sub. All right, so this is our first example of substitution here. And really what's probably the most confusing here is just this U and DU. And it is really just a notation thing. So we'll do a handful more examples just to get really used to it. So let's take a look here. We're going to now look at this example, and this integral looks a lot more complicated than anything that we've ever done. So I have the integral of 3x squared multiplied by the square root of x cubed plus 1. So let's go ahead and bring this onto a new page here. 3x squared square root of x cubed plus 1 dx. So at this point here, it might not be so obvious how we should do our substitution. Hopefully it's clear that this integral is tough enough, it's complicated enough that we're not just going to be able to use like the power rule very explicitly. We're not going to be able to use an exponential or a logarithmic rule. Those don't even apply here because we don't have exponentials or logs. But in this case, the power rule is just, I mean, that's just, again, it's just for x to the n. And this definitely doesn't look like that. This is a lot more complicated. So my goal is to write it in that format, but I got to use substitution to do that. So what's tough here is actually trying to come up with what u should actually be. And I have a couple options here. I could presume that u could be 3x squared. I could guess u could be x cubed plus 1. I could guess that u is equal to, let me go ahead and write these vertically. It'll look a little better. I could guess that u is equal to x cubed. I could even go complicated and I could say u is this entire square root. Any of these seemingly could work. And where I'm at right now is I don't necessarily know which one is going to work. And so really it boils down to try them. It's just a guess and check method for finding out this u. We'll end up seeing more complicated problems where you really aren't sure what to use for u, and you really just have to try things out and hope it works. If it doesn't work out, come back to this step and try something different. What are sort of a general idea, a general sort of guideline for picking u? A lot of times it's something that's all paired together and maybe underneath, maybe inside a power or something like that. For example, on this past example here, we had the 2x plus 5 that was all being raised to the 7th, so I replaced u with that. Going back even further to here, I noticed the 7x plus 1 is all in the exponent, so I might make all of that be u. And so here, I've obviously done this problem before. I am showing you now. I know that this is going to be our u. And with time, with practice, you'll get there too. Let's go ahead and work it out. We'll see that it works. I highly recommend trying all of those options that I just erased. Try them and see if they work. See how they don't work, I should say. So here we're going to set u equal to x cubed plus 1. And while this is all fine and dandy, we still have x's in here. Yeah, I can replace what's underneath that square root with a u, but I still have the issue of this x out here and this dx out here. And that's where let's go ahead and erase that because we don't want any of that yet. That's where my du will come in. So I'm going to take a derivative of this x cubed plus 1. I'm going to get 3x squared, and then don't forget that dx that's out front. Make that look a little nicer. All right. And now at this point here, what we did on the last problem was we did du divided by 3x squared equals dx. We divided that 2 over, if you recall. Here, I actually don't need to do that because I'm actually already at the point where I say, hey, look, here's a 3x squared dx that I've weirdly boxed. Here's a 3x squared dx. 3x squared dx is just du. I already have it. It's very explicit right there. So what I can do is I can replace, and I'm gonna be very careful about how I show this replacement. I'm gonna underline things that replace each other. So in the red there, you can see that x cubed plus 1, that's just replaced by u. We've got it written in the orange, u is equal to x cubed plus 1. So that's fantastic. We have a square root of u. And then you see in the purple, it's just explicitly written right there. 3x squared dx is equal to du. So we replace it with du. And ta-da, our integral has now changed from an integral in x to an integral in u. And this is an integral that we can very easily work out with the power rule. I'm going to rewrite that, the 1/2. And now when I do the power rule here, I'll just add 1 to that exponent. And notice that I'm adding 2 over 2. So I'm doing 1/2 plus 1, which gives me 3/2. And I divide by that 3/2. I still have a plus c. That division by 3/2 is the same as multiplication by 2/3. So I have u to the 3/2. And again, as before, we're not quite done. I have to take that u and I have to replace it with what it's equal to in terms of x, because our original integral was in terms of x. So I need to have my final answer also in terms of x. And so you can see right here, there you go. We've got our answer. Yet again, if you take a derivative of this answer, you should get 3x squared square root of x cubed plus 1. That's always something that you can do with integrals. You can always check your answer very easily by just taking a derivative of it and seeing what you get. Obviously, you have to take the derivative carefully and correctly, but that's a way you can check your answer. So in this case, this kind of worked out perfectly. Our purple here, it just was replaced super easily. So let's go ahead and let's take a look at an example where it doesn't replace super easily. So let's go ahead, we'll skip past all this, I've done all that. Let's take a look at this integral, x square root of x plus 1. So in this case here, again, we have options that we can pick for u. So we have the integral of x square root of x plus 1 dx. I'm gonna try this. I'm actually gonna start off. I'm gonna say, hey, you know what? I've got an x sitting right out front there. I'm gonna just set u equal to x here, and let's go ahead and try this. So if u is x, then du is 1 dx, which I can just write, hey, du is dx. And so let's go ahead and do this. Let's do our replacement where dx here is going to be replaced with du. And then I'll mark this in the red. The x is going to be replaced with u right there. And so when I take this, I'm going to say, all right, I have an x in red. Let's replace it with a u. I have my square root. And then I have an x in red. Let's replace it with a u plus 1. And then instead of dx, I have du. Well, when I look at these integrals, let's go ahead and get rid of these colors here. When I look at these two integrals, they look identical to me. Obviously, x versus u, right? I'm using a different variable, but the integral is the same. It doesn't just, if I just changed all these u's back to x's, it's the same exact integral. And this leads me to a point that really has nothing to do with this specific integral, but this is a point that I want to make. You should never bother with the substitution u equals x. It doesn't do anything. Because if u is equal to x, then du is equal to dx. And all you're doing is you're just changing the letter from x to u. So this is never a substitution that you should bother with. Obviously, if you do it, you're just going to get right to here. And now you just are right back where you started. So we won't bother with that. Let's not bother with u equals x. But as you can hopefully see here, I do want to make u equal to x plus 1. You might try to do u equals square root of x plus 1, but you'll find out pretty quickly that that doesn't really help us. So we have u is equal to x plus 1. Du is equal to dx. And this is great, right? We have our square root of u. We have a du. And notice I'm replacing that x plus 1 with a u. I'm replacing dx with du. But now my issue here is that I have x. And so we run into this problem here where how do I get rid of that x? And here we have to get a little bit clever. So this is where that sort of thought process of thinking of u as a function of x is helpful. If u is a function of x, what I could do is I could take this and I could solve it for x. You notice if I subtract 1 from both sides, then I end up with x equals just u minus 1. Now I have x written in terms of u. And so what I can do here is instead of, let me give myself some more space here. Instead of an x, I can go ahead and write u plus 1 right there. Just kind of squeeze that in. And now my integral is only in terms of u. And this is good. That's what we like. So continuing on, we'll distribute here. U to the 1 multiplied by u to the 1/2 is u to the 3/2, plus 1 times root u is u to the 1/2. And then simple power rule applies. So I'll do this a little bit quickly just because we've got multiple of them. So I'm going to have 2/5 u to the 5/2 plus 2/3 u to the 3/2, and don't forget our plus c. And then also don't forget we want to replace this with x plus 1. And as we always used to do with derivatives, we might want to simplify this a bit more. There's definitely some factoring that I could do here. For example, I could factor out a 2 times x plus 1 to the 3/2, and then I'd end up with a 1/5 times x plus 1 plus 1/3 plus c. And I could do more simplification here, simplifying this down. I'm not going to bother with that for now. This is simplification that you should do. We always want to write our integrals as simple as we can, but for now, I'm just going to save some time and not bother because we just have some simple algebra here, simple fraction algebra and addition there. So we'll go ahead and move on, but we've got our answer. And we obviously had to do this little roundabout way of, hey, taking our remaining x's and writing them in terms of u. But that's a method that we might see moving forward. All right, let's go ahead. We're going to do just a couple more examples and then we'll wrap this up. So I want to do this integral example, x plus 3 divided by x squared plus 6x. This is a great example where it's maybe not so obvious what we should use for our u. We could try using u equals x plus 3. And if I do that, du is going to be dx. And this is great in the sense that I can replace that and that. But I don't have any way of replacing the x squared plus 6. There's not really anything I can do here to get rid of that. And so that's going to yield an issue. We don't want to do u equals x plus 3 there. We're going to want to try u equals x squared plus 6x. So my du is going to be 2x plus 6 dx. Make sure to put a parentheses there. That's important. And now here again is where we have an issue. So in this scenario, I do have a way of replacing the x squared plus 6x. I have a way of replacing the dx, but this doesn't match up perfectly with that x plus 3. If you remember a couple examples ago, we had that example with the 3x squared square root of x cubed plus 1. And when we did u was equal to x cubed plus 1, we just kind of got lucky and happened to get exactly that 3x squared that we're seeing up here. And so we got lucky. But here we don't actually have that. Here we have a 2x plus 6, and here we have an x plus 3. So now we got to get a little bit clever, and we got to hope that we can sort of fashion out an x plus 3 from where we're at. And so what I notice here is I can factor out a 2, and there's my x plus 3. So now let's divide both sides by 2. We'll have x plus 3 dx. And now my substitution just works very nice and neatly. In the red right there, and then in the purple right there. So we'll end up with, notice on the numerator, I have all my red. So the numerator, I'm going to have a 1/2. I'll put my du over here. And then I have that purple in the denominator. So it's going to be a 1/u. So this ends up just simplifying this to 1/2u. Well, let's go ahead and do this actually. Let's pull that 1/2 out front. 1/u du. And from here, this is just a simple logarithmic integral. We never forget our absolute value here, ln of absolute value of u plus c. And then last step here, replacing that u with x squared plus 6x. And we end up with our answer right there. All right, so there's an example of a u sub where when you do your du, you don't explicitly get what's in the integral. You kind of have to do a little bit of algebra. You got to do some work there to figure out how to get that out. Let's go ahead and do one more example. And so here, we're going to go ahead and look at the integral of x. No, I'm going to do a different one, actually. Let's do e to the square root of x over square root of x dx. This one definitely looks complicated. To me, I see a square root of x there. I see a square root of x there. My initial instinct is, all right, square root of x appears multiple times in here. Let's do u equals square root of x, because then I can just get rid of all those square root of x's with just nice simple u's. And so when I take my derivative with a little bit of power rule, you can get 1/2 square root of x. And again, I don't see this explicitly in my integral up above. I do see the dx, it's right there. I don't see this explicitly, but what I do see is I see that. And notice I'm not boxing that 2, but I see a 1/√x right there. And so what I want to do here is I want to actually multiply this 2 over so that I have 1/√x dx. And now again, we'll use our colors. Purple is this dx over square root of x. That's just a 2 du. And then my root x here is the u. And so we end up with integral of e to the u and then multiplied by 2 du. And again, we're all in terms of u, so that's good. That's helpful. I can bring the 2 out front. E to the u du. This is a simple exponential integral because it's e, base e. We just leave it exactly as it is. Don't forget, u is square root of x, so we replace that back in, and we've got our answer there. All right, so you've seen several examples there. The tough parts about this u sub are definitely the notation, u, du, and dx, and all that. The other tough part is figuring out what u actually needs to be, and that's really a guess and check method. We'll see several examples where you might not be sure of what to use there, but you just try them all and see which one works out. And then we've seen that other thing where we don't really bother setting u equal to x. That just doesn't really do us any good here. What also will be tough is to actually, in the future, figure out whether or not you need to use substitution. In some cases, you might not even need to. But for now, we'll be dealing with substitution, so you'll be using it a lot. So that'll be it. That's the last example I'm going to do, and we'll go ahead and call that the lecture.